During powerful sandstorms, the top of the Burj Khalifa can sway by nearly 6 feet. That may sound alarming, but an even more surprising system lies beneath the building. Its foundation requires a continuous DC electrical supply. Without this protection, corrosion could gradually weaken the foundation. The reason lies in Dubai's challenging ground conditions. Excavating desert soil is extremely difficult because the loose surrounding material can continuously collapse back into the borehole. This type of ground is also highly susceptible to settlement. When a heavy building is constructed, its weight compresses the soil beneath it, causing the structure to move slowly downwards. Excessive or uneven settlement can create cracks and, in severe cases, lead to structural failure. However, loose sand was not the only challenge faced by the engineers. They knew that the enormous weight of the Burj Khalifa could not be supported directly by the surface soil. Ideally, this load would be transferred to hard strata, a strong underground rock layer capable of carrying extremely heavy loads. Engineers drilled exploratory boreholes to depths of approximately 140 meters at several locations. However, they found no sufficiently strong rock layer beneath the site. They therefore adopted a different solution based on friction. Imagine driving a steel rod into loose sand with a hammer. At first, it moves down easily. As it penetrates deeper, however, the surrounding soil grips it more firmly until further movement becomes extremely difficult. At this stage, the force is no longer transferred only downwards. It is also distributed sideways into the surrounding soil. The friction along the surface of the rod becomes strong enough to resist further penetration. Engineers realized that the same principle could be used beneath the Burj Khalifa. Instead of relying only on support from below, much of the building's load could be transferred through friction along the sides of deep foundation piles. A thick concrete base known as a raft was constructed above the piles, approximately 3.7 meters thick. It collects the load from the entire building and distributes it across the pile foundation. Constructing these piles presented another major challenge. As the auger drilled into the loose ground, the walls of the borehole could collapse inwards, making it difficult to maintain a stable excavation. To solve this problem, a steel casing is first placed at the surface, and polymer slurry is poured into it. The auger then removes the soil while the slurry fills the empty space behind it, acting like a liquid support. The slurry applies pressure to the borehole walls and prevents the surrounding soil and groundwater from collapsing into the hole. Once the borehole reached the required depth, a steel reinforcement cage was lowered into position. However, because the borehole was still filled with slurry, the concrete had to be placed using a specialized method. Using the Tremie method, concrete was pumped through a long pipe directly to the bottom of the borehole. As the concrete rose from below, it displaced the slurry upwards towards the surface. Using this method, engineers constructed 192 foundation piles. Each pile is approximately 43 meters long and 1.5 meters in diameter. After construction, the piles underwent extensive load testing. Test loads of up to approximately twice the expected working load were applied, while engineers carefully measured their settlement. Even after the building was completed, the total recorded settlement was only around 5 centimeters. Steel reinforcement was then installed above the piles to form the raft. Because the raft was too large to cast in a single pour, the concrete was placed in separate sections beneath the 3 wings, followed by the central section. The Burj Khalifa's floor plan was inspired by the shape of a flower. Around the raft at the lowest level are the building's basement and parking areas. The Burj Khalifa was not designed to resist powerful winds through brute strength alone. Instead, its form disrupts the airflow. Central to this strategy is its hexagonal structural core. The core contains the public lifts, service lifts, and staircases. The usable floor space is arranged around this central structure. Its construction was carefully engineered and carried out by Samsung C&T. At such an extreme height, however, the central core alone could not safely resist wind and earthquake forces. It is therefore supported by 3 structural buttresses, similar in principle to the supports used in dams to resist lateral pressure. Rather than using visible external supports, engineers formed the buttresses as stepped internal walls. The spaces between them were incorporated into corridors, allowing the structural system to become a functional part of the building. Cross walls and columns extend along the sides of the buttresses, with the external facade attached around them. However, these walls do far more than simply support the exterior of the building. When strong winds strike the building from one direction, the force acts mainly on two wings, while the third wing helps brace the structure from behind. When the wind direction changes, a different combination of wings resists the load. Unequal forces across the structure can still cause the tower to bend slightly. A limited amount of movement is normal, but excessive bending creates tensile stress that concrete cannot withstand effectively. Steel reinforcement inside the core helps carry this tension and allows limited flexibility. The cross walls and beams then work together to reduce deformation and distribute the forces throughout the structure. Many tall buildings use tuned mass dampers to reduce movement during earthquakes or strong winds. The Burj Khalifa, however, primarily relies on its buttressed core, cross walls, and interconnected structural elements to resist forces from multiple directions. Inside the Burj Khalifa, the cross walls, beams, and floor slabs form a highly interconnected structural system. By working together, they improve the tower's overall strength and stability. The Burj Khalifa is not perfectly symmetrical. Its three wings terminate at different heights, while the tower gradually narrows towards the top. This irregular form serves an important aerodynamic purpose. If the tower had a uniform symmetrical shape, wind flowing around it could create alternating zones of low pressure behind the structure. These pressure differences would produce rotating air currents known as vortices, causing a phenomenon called vortex shedding. Vortex shedding can make a tall building oscillate from side to side. If the frequency of these forces approaches the building's natural frequency, resonance may amplify the movement. A spiraling and progressively changing shape helps prevent this regular airflow pattern from developing. If you look closely at the Burj Khalifa, you'll notice its spiraling form. The wings end at different angles and heights, creating a gradual spiral. This prevents vortices from forming in a regular pattern and greatly reduces vortex shedding. In simple terms, the design breaks up powerful winds before they can make the tower vibrate. At regular intervals along the Burj Khalifa, special mechanical floors can be seen. These levels contain essential systems for electrical distribution, lift operation, water supply, air conditioning, and building safety. As the tower rose higher, engineers faced another major challenge. How could concrete be transported to such an extreme height? The concrete was prepared at ground level and fed into high-pressure pumps. Inside each pump, two pistons worked alternatively to force the mixture upwards through the pipeline. It took approximately 40 minutes for the concrete to reach a height of 600 meters. This creates a serious temperature control problem. Dubai's climate was already extremely hot, and heat generated during pumping could cause the concrete to set prematurely inside the pipeline. To keep the mixture cool and workable, ice was added during production. The Burj Khalifa was not originally planned to reach 828 meters. However, its structural design allowed the tower to be extended further. Reinforced concrete was used up to approximately 606 meters, while the upper section was constructed from steel. This steel structure extended for roughly 202 meters and contains no lifts. During powerful sandstorms, the upper steel section can sway by around 6 feet. A lightning protection system is installed at the top of the Burj Khalifa. Because of the tower's exceptional height, it frequently intercepts lightning strikes and acts as a prominent lightning receptor. When the system detects a highly charged cloud, it produces an opposite electrical charge that helps attract the lightning strike. The resulting current then travels safely down the building and into the ground through the foundation's reinforcement network. The most unusual system lies beneath the tower. A continuous low-voltage DC supply is used to protect parts of the foundation because the deep piles are exposed to highly saline groundwater. Steel reinforcement is normally protected by the surrounding concrete. However, if chlorides from saline groundwater penetrate the concrete, corrosion can begin. Over time, this may reduce the strength and durability of the foundation. To control this corrosion, the foundation uses an impressed current cathodic protection system. A low-level positive DC connection is applied to a titanium-based anode mesh, while the steel reinforcement is connected to the negative terminal. This process is similar to electrolysis. Electrons move towards the cathode, which is the steel reinforcement, protecting it from corrosion. The corrosion is shifted to the anode instead, so the anode gradually wears out and must be replaced after a certain period. Share your thoughts in the comments and subscribe to the channel for more informative engineering videos. Thank you so much for watching.